Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at question 23 on our 2011 Fermat paper. And I must say, they really seem to like this question, this Dolly, Molly, and Polly question, because it was on the Pascal for question 25. I think it was question 24 on the Cayley, and now it's question 23. So it's just sort of moved up one each time. They really liked it, so I went through it very slowly, and if I recall correctly, I ended up screwing up my calculations a little bit when I did this for the Pascal. I did it a little faster for the Cayley. Now we're at the Fermat. I'm going to do it a little faster because, honestly, this is the third time I've done this question. So if you're looking for a slower approach to this, take a look at my Pascal or my Cayley version of this. As I say, 25, 24, I'm pretty sure those are the numbers, where I go in a little more detail to the strategy. But this is the Fermat paper, so I think we can talk a little bit more about this, or talk about this a little quicker. That's what I'm trying to say. Anyway, Dolly, Molly, and Polly can each walk 6 kilometers per hour. They've got a motorcycle that can go at 90 kilometers per hour and can hold at most 2 of them, but cannot drive by itself because, of course, this was written in 2011. Autonomous cars or motorcycles were not really a thing back then. Not that they particularly are at the time of recording, but at least they're somewhat possible now. Anyway, let t hours be the time it takes for all 3 of them to reach a point 135 kilometers away. Ignoring the time required to start, stop, or change directions, which is fairly common in a contest question like this, what is true about the smallest value of t? So we want them to get there in the smallest amount of time, and then they're giving us some ranges, some options here. Okay? So they're not asking us for t exactly. They're asking us for, what could t possibly, where could it fall? It might be particularly large, it might be particularly small, or maybe for some reason it's between 4.1 and 4.3. Who knows? Well, I do, because I said I've done this one twice already. But okay, how do we approach a question like this? Well, I find a picture can particularly help. So I might draw a little picture of Dolly, Molly, and Polly starting here, and then there's where they want to get to at the end, 135 kilometers away. Okay? So there's lots of ways to do this. There's various strategies that you can explore, but the most efficient one, and by efficient I mean the one that's going to give us the lowest time, is one where everybody arrives at the end at the same time. Okay? We don't want Dolly to be sitting around at the end waiting for Molly and Polly to catch up. Okay? So you could think of it sort of like, the most naive strategy would be Dolly gets on the motorcycle, ferries Polly to the end, and then comes back for Molly, and drives her to the end. That's okay, but you got Polly sitting around doing nothing, and you've got Molly sitting around waiting and doing nothing. Surely Molly could be walking a little bit in this time, and that reduces the amount of time that Dolly needs to come back to pick her up, reducing Dolly's overall journey and thus speeding things up. And if you make that connection that Molly could be walking, well, who says we got to drop Polly all the way off at the end? Maybe we drop Polly off a little bit towards the end, and that reduces the amount of time Dolly needs to come back to get Molly, who's been walking. And maybe in this time, Polly walks all the way to the end. And it turns out this is going to be the most efficient. Everybody is walking or moving at every given time. There's sort of no way to speed things up. There's no excess. There's no waste. There's no one sitting around waiting to be picked up or waiting for everyone to show up at the end. Okay, so understanding that that's going to be the best strategy, we need to start figuring things out. Like, well, where do you drop Polly off to make this all work out? Where do you drop Polly off to make sure that everyone gets to the end on time? All at the same time. Because if some people are a little early, if the motorcycle gang's a little early, then we should have dropped Polly off a little later. If Polly gets there and is sitting there twiddling her thumbs waiting for everyone else, then we could have dropped Polly off a little earlier, made her walk a bit further. Okay? Again, we don't want any waste. And that's how we think about this, and that's how we arrive at our best strategy. So, what could we do? Well, we could say, let's drop Polly off P from the end. Well, no, actually, that might get confusing, because little p and capital P look the same. So we'll say K from the end. Okay? And so we'll drop Polly off k from the end, and so Polly's going to walk k till the end, and that'll be at a distance k. So where do we place k? And then after we figure that all out, we need to find the answer, t. Well, t will be the hours it takes Dolly to drive Polly all the way here. So that many kilometers over that many kilometers per hour, plus the time it takes Polly to walk, and that'll be k kilometers at 6 kilometers per hour. So that will be t. That's what we need to work out there. Okay? Now, you could say, well, get a common denominator of 90 here. You'll get 135 minus k plus 15k. So t will be 135 plus 14k all over 90. Okay? So, but we still need to figure out this k. Where exactly do we drop Polly off from the end? Okay? You know, you can see if k is 0, and then we go back and get Molly and everything, that's fine, but that's not the most efficient. The most efficiently the plan I have described. So, we know it takes 135 minus k over 90 hours to get Polly to the drop-off. Now, in that time, Molly has been walking at 6 kilometers per hour. So in that time, Molly has gone 135 minus k over 15 kilometers. So Polly's been dropped off, and now Molly is sitting here and waiting for Dolly to come back and get her. So how far does Dolly have to go? Well, Dolly's coming back towards Molly. Molly continues walking at 6 kilometers per hour. Dolly's speeding along on the motorcycle still at 90 kilometers per hour. So effectively, the distance between where Polly gets dropped off and where Molly is when Polly gets dropped off is shrinking as these two get closer to each other, and that's shrinking at a rate of 96 kilometers per hour. Okay? So, what can we do here? We also have to ask ourselves, well, you know, is there some sort of argument we could make, some sort of symmetry argument here? And this is me trying to add a new twist on it, because as I say, I've done this question twice already. I'm just trying to think of new strategies for approaching the question. And so one thing I thought is, or one thing I'm currently thinking is, okay, so we drop Polly off, and Molly has walked a certain distance. And then Dolly comes back, gets Molly, and then they go to the end. Right? And then Polly has met them there. But if we play this scenario in reverse, it's Dolly and Molly going backwards, dropping Molly off somewhere. Right? Dropping Molly off somewhere, and then Dolly rides backwards and picks up Polly, who's been sort of walking backwards to this point. And then they, again, on their motorbike, going backwards in time, arrive at the same place as Molly. Okay? So, there's this sort of symmetry that you can reverse the argument a little bit. So, where are they going to meet? Well, they're going to meet a distance k from the end, again. There's this nice symmetry argument. You know, you don't view it so much as Dolly coming back to pick up Molly, as you view it in reverse, Dolly and Molly driving backwards and dropping Molly off, and that must be k from the end. So, where do Dolly and Molly meet or part ways, depending on your perspective? Well, distance k from the start, really. Okay. So, how long has Molly been walking before she's picked up? Again, distance. It'll be k over 6. Now, how exactly might this help us? Well, trying to think of a way for that to help, because it's a nice observation. I'm not exactly sure it'll fit somewhere in here. Okay, but it is worthwhile to be considering these things. So they meet at 90. No. So no, they meet at k. I can't express it in terms of 90 or 96 or anything like that. And then they drive to the end. So I think it's important to figure out how much time Dolly must be driving for. So this is a distance case. So she drops off Polly at k, then she meets Molly at k. So that'd be 135 minus 2k. And that's how long, that's how far Dolly drives the motorcycle. And so that distance, or that time, yeah, so what does Dolly do? She drives 135 minus k to drop Polly off, and then she comes back 135 minus 2k to meet Molly. And in that time, Molly has gone k kilometers. Okay? So this symmetry argument, I didn't do this for the Pascal or the Cayley. This is sort of a new argument because I wanted to make this fresh for me. So in the time it takes Dolly to go 135 minus k plus 135 minus 2k, and that's at 90 kilometers per hour, Molly will have gone k kilometers at 6 kilometers per hour. So I'll multiply both sides by 90. We'll get 270 minus 3k is 15k. So 270 should be 18k, and now we can very quickly find k, whereas when I did this with the Pascal and the Cayley, it actually took me a little while to figure out k. So looking for this symmetry argument is really, really nice. So divide both sides by 9. You'll get 30 is equal to 2k. And so we'll get k is 15. So 15 kilometers is where Polly is dropped. So 15 kilometers from the end is where Polly is dropped off. 15 kilometers from the beginning is where Molly is picked up by Dolly. Okay? But we have an expression for t, right? So t is minimum time, because we're being very efficient, is 135 plus 14 times 15, because that's our k value, over 90. Wait, it was over 90, right? Yeah, over 90. Okay, well, I can divide by 15 on top and bottom, so you'll get 9 plus 14 all over 6. And so we'll get 23 over 6. That should be our minimum time. Okay, and so 23 over 6 is about 3.833. Now, even if this wasn't the best answer and I completely had botched the idea, this is the smallest of the presented intervals. This is A, so we don't actually have to do any further work. But this is the fastest time possible. 23 over 6. Okay, so there's question 24. It's a little different than how I did it with the Pascal and the Cayley. I did it a little faster, and I tried to use this interesting little symmetry argument that had me stumble for a moment, but this has come up more than once. Not this question, but this symmetry argument. I remember I was doing a Euclid contest recently. I think it was the 2015 or the 2016 paper. And then there was about these people who were swimming and paddling a canoe across a river, and it was the same sort of thing. You could do a little symmetry argument to cut down on a lot of the calculations. So it's kind of nice. Play these scenarios in reverse, and you can make an observation. Because I didn't make the Molly goes a distance k observation when I did this earlier. It's kind of nice. Kind of nice. A lot easier to calculate with. Okay, we've got one more question to go. That'll be question number 25. Wait, no. This is question 23. We've got question 24 and 25 to go. So up next will be question number 24. I will see you for that as we continue our Fermat paper. Until then, have a wonderful day.